Imagine trying to teach a machine to identify a flower. You can't show it a picture, and you can't give it a hard-coded rule. We have 3 specific targets: setosa, versicolor, and virginica. To a botanist, the physical patterns distinguishing these species are obvious, but our machine operates completely blind. Its entire perception of these plants is restricted to a simple dataset, containing exactly 4 numbers per flower: sepal length, sepal width, petal length, and petal width. To identify the species, the machine must derive the hidden mathematical boundaries separating these 4 floating point numbers. This is where the k-nearest neighbors, or KNN algorithm, comes in. It relies on a very simple physical intuition. Things that are similar to each other naturally exist close together in space. We start by taking our known training data and plotting it. Every flower's 4 measurements dictate a single coordinate on a map. Then, a newly discovered mystery flower drops onto this map. It has specific measurements: 6.2, 2.9, 4.3, and 1.3. But right now, this map is warped. Because raw petal and sepal measurements span completely different numeric scales, larger numbers forcibly stretch the grid, making accurate distance calculation impossible. When we rely on unscaled data, larger numeric magnitudes dominate the geometry, leading to biased and incorrect classifications. To correct the spatial map, we apply feature scaling. We run the raw numbers through a standardized scaler, a mathematical operation that forces all 4 flower measurements into comparable, standardized ranges. We lock this step inside a pipeline. This ensures the scaler only ever learns its parameters from our initial training data, keeping our future test data isolated so it shall not contaminate the model's environment. Enforcing this uniform geometry before any math happens prevents a single feature from unfairly dominating the algorithm just because its numbers are larger. With the space corrected, the algorithm finally measures the physical gap between our mystery flower and the known dataset. We tell the model to use the Minkowski distance formula with a parameter of p equals 2, which calculates a direct, straight-line Euclidean path between the points. But the algorithm needs the limit for its search radius. This is the hyperparameter k. We set k to 5, instructing the algorithm to expand its geometric search outward until it captures exactly 5 neighboring points. Now, a vote triggers. Those 5 captured neighbors cast a ballot based on their own species, and the simple majority dictates the prediction. Based on the surrounding geometry, the algorithm confidently classifies the mystery flower as a versicolor. The final prediction is the result of a localized democratic consensus dictated by rigid physical distance. That works for one flower, but to test overall reliability, we run a hidden test batch, representing 25% of our entire dataset through the system. Using our baseline of k equals 5, the model successfully classifies 92% of the test samples. To find exactly where geometric logic failed the remaining 8%, we use a confusion matrix. The matrix exposes a biological reality. While setosa flowers are isolated and easy to group, the traits of versicolor and virginica mathematically overlap. That blur creates 3 distinct errors, where virginica samples are mislabeled as versicolor. Overlapping biological traits create zones of mathematical ambiguity, masking localized structural weaknesses in a model. We can sharpen that blurred boundary through hyperparameter tuning. We iterate through a sequence of new tests, turning the k value from 1 up to 15 to see how the model adapts. This chart tracks how test accuracy fluctuates in response to k. A tiny k is too sensitive to outliers, dragging accuracy down, while a large k smears boundaries. The data reveals an optimal plateau between k equals 9 and 13, where accuracy peaks. Effective classification relies on rigorous data standardization, careful geometric mapping, and systematic tuning to draw sharp boundaries through natural chaos.